Okay, so we're going to be going over the 28th problem in the grind 75. This is k closest points to origin. So we're going to be going over the solution. And basically we are given an input array of points. So an array with arrays of two elements, where the first one represents the x-coordinate and the second one represents the y-coordinate. And basically we want to get the k points that are closest to the origin. So conceptually, this really isn't too bad. They actually tell us the way to figure out the distance between 2 points. And so all we have to do is iterate through the entire array and calculate the Euclidean distances. And this is actually scratched from the last work. But basically, we use a priority queue to order our points by their distance. And a priority queue is naturally at a max heap, and that actually works in our favor. And the way we can make this work in this problem is basically when we find a point when we're iterating, we add it to the priority queue, and as soon as our priority queue is greater than the number of points we want to find, then we can just pop off or pull that top value of the priority queue because it's a maximum value. And basically when we go through the entire array, we're going to be adding, and every time we hit capacity, we're going to be taking off that maximum value. And so once we hit the end, we're going to be left with the k points with the smallest value, and meaning that they are closest to the origin. And while this formula is probably very easy to implement in Python, there's a lot of things that sort of go wrong if we try to do it, implement this formula verbatim in Java. For example, the square root function is used for doubles and not for ints, so there's some loss that can happen when we're converting from a double to an integer. So what we actually have to do is create a comparator class, and that's because we want to add values to the priority queue based on some value that is not immediately apparent, right? We need to calculate the distance, right? So first off, let's just start off by creating our priority queue. So that's going to be a priority queue consisting of those two element integers, which represent points, and we can just call it PQ. And we're going to set it equal to a new priority queue of the same type, dynamic type as static type. And one of the constructors of priority queues can take in an initial capacity, which will be k, and then a comparator object, which we will actually create ourselves. So I'm just going to say new filter. That's what we're going to call our comparator object. And right now I'm actually going to define the comparator object. So the way that we create comparator objects, they're objects, so they're a class. We have to create a class, and we can call it whatever we want. I'm just calling it filter. And then we have to implement the comparator interface, and we have to pass into this comparator the type of objects that we will be comparing. Okay, so we've created this class inside of our class, but we will have access to it, inside of this method because we're in one class. And what we want to do, and this is pretty important to get all of this right, we need to override the public method compare. And we want to return an integer because compare basically boils this down to an integer. So when the priority queue is looking at it, it's just going to take the biggest integer, put that on top, right? That's what makes the most sense. So we need to convert what we have into an integer representation. So that's basically going to be the distance. That's what we want to compare by. So we need two values when we're comparing. And what we're going to do is return this right here. We are going to return the x component squared of the second pair plus the y component squared also of the second pair. And I'm going to wrap these in parentheses. We're going to say minus the same thing, but now we're going to take the, let's see, we're going to take the first pair's x coordinate, square it, and add the first pair's y coordinate, square it. So the reason why we have two integer pairs, or in this case points, is because for comparators need to compare two separate things. And essentially why this works for this problem instead of doing this formula right here, we'll illustrate in Paint. So this is what the formula is, but since we're trying to get the point that's closest to the origin, we can imagine that x2 and y2 are equal to 0, so they don't exist. And so what we get is this right here. And this is almost what we have in the comparator. We have the point's x coordinate squared plus its y component squared, but we are missing that square root part right here. So is that okay? Do we need that square root part? Well, it turns out that we actually don't. And if we look at a graph of x squared and x, if we have two values, two integer values, say they're here and here, what we actually want is their square values, but we'll notice that the square values will always be in the same relation to the origin as the regular x values, as long as these values are integers, right? Because you see in this case, the non-squared value is actually above the squared value. We don't have to worry about this case because we're simply dealing with integers. And again, negative integers, once squared, will become their positive counterparts anyways. So that's just a little intuition as to why this works. So we should be able to return that. Okay. And that's probably the most complicated part. From here, it's smooth sailing. So indentation is weird occasionally. So what we have to do now is add to our priority queue. So we're just going to say for integer array point in points, we are going to, all we have to do is nice and easy dot add. But if we get to the point where the priority queue is greater, then it can, the priority queue has more points in it that we want than we want to return, then we're going to simply remove that top one, because again, it's a max heap, and so we can get rid of those larger values because we want that smallest distance. So pq dot remove. Okay. And at this point, we will have a priority queue that has all of the points with the smallest distance, but what we want to return is an integer array of those points represented as integer arrays. So what we can do is create one of those, call it result, set it equal to an integer array of size k, where k is, again, the number of points we want, and each element will have two values, the x and the y. And we are just going to say for int I equals 0, while I is less than our value of k, just going to increment I, we are going to say result at index I is equal to pq dot poll. We can also do remove, but poll essentially is like pop for a stack or like a queue. So we can do poll, and yeah, that should be it. We'll be adding to the proper indices, and then at the end we can return result. Okay, it should be right unless we have some syntactical errors. Let's see. Implements. Should be implements. Okay. All right, and that has been the solution to the 28th problem in the grind 75. As for the time complexity of this algorithm, we know that we're going to have to touch every point in points. So that's already an O of n operation. N represents every element in points. But we are also going to have to add to the priority queue. And every time we add to the priority queue, the worst case is that we will have to travel down the priority queue all the way to the bottom. As in, if we insert a minimum value, we know that's going to be pushed to the bottom because the priority queue is a max heap. And so that's going to take log k of time, log k time. So our total operation for inserting to the priority queue is log k of time, and then because we have to do that for every point in points, the time complexity of this algorithm comes out to n log k.